In this video, we're going to look at the calculus with vector-valued functions. In other words, how to do calculus topics with vector-valued functions. So recall we looked at these in a previous video. A vector-valued function in R2 or R3 is a function that takes inputs that are real numbers and has outputs that are vectors. And each component of our vector is going to be determined by a function of t, where t is the input. A lot of times when we think of this variable t, we think of it as time, but you can think of it as lots of other things too. So r of t is going to give out a vector, and each component in the vector is going to be a function of t. If you think about that and how calculus operations will work, well, calculus operations, generally speaking, will work the way you think they should. When we deal with limits, when we deal with derivatives, when we deal with integration, it's going to work the way that's natural. It's going to be like applying a limit to a vector, so we apply it to each component of the vector. It'll be like applying the derivative to a vector, so we apply the derivative to each component of the vector. It's like we integrate a vector, which means we're going to integrate each component of the vector. So let's start out with limits. Now I'm writing this in R3, so let's pretend I have a vector-valued function r, which is in the real numbers, the three-dimensional real numbers. But you could easily just do this on R2 as well. So if I take the limit of a vector-valued function as t goes to the number c, then we just need to apply that limit to each component of the output. So limit as t goes to c of our vector-valued function is equal to the vector limit t going to c of f, comma, limit t going to c of g, comma, limit t going to c of h. So we basically take the limit of each of those components and apply and calculate. So let's go ahead and do that a couple of times. Let's take this vector-valued function and we'll find the limit as t goes to 5. We'll find the limit as t goes to 4. We'll find the limit as t goes to -2. And we'll find the limit as t goes to 0. So here we go. Let's start by taking the limit of the vector-valued function as t gets closer to 5. So what I'm going to do is I am going to take the limit of each of these components as t gets closer to 5. So t, right arrow, whoops, 5. We'll do that in each of these, t going to 5. And then we'll do that over here too. Okay, so taking the limit as t goes to 5, on the y component and on the z component, all I have to do is plug in 5. Those are continuous, close to 5, so I just plug that in. Now on the x component, that's a little bit different. So what I'll have to do on the x component is a little bit of algebra, but let me go for the y component first. Since, like I said, those functions are continuous at 5, all I have to do is plug in those numbers. So plug in 5 in for t here and here. And then on this one, plug in 5 in for t there. Now, as far as the limit on the x component, this can be found, but I need to do some algebra on that. So what I would do is I'd factor the numerator, t squared minus 3t minus 10. I'm not going to show how to factor, but it's basically something I'm sure everyone has seen. T plus 2 times t minus 5 is what you get in the numerator. And in the denominator, we have t minus 5. So notice that these t minus 5s are going to cancel out. So that going to cancel out with that. That'll become 1, and you'll just be left with a t plus 2. And in the t plus 2, you can just simply plug in the 5. And so what you're getting is that this limit, the limit as t approaches 5 of my vector valued function, is equal to, well, this first limit becomes 7. So 5 plus 2 becomes 7. The second component becomes 5 squared plus 4 times 5. That's 45. And the third component becomes 6 over 5 plus 2, which is 6/7. Whoops. Uh-oh. Oh, I hit the wrong button. There we go. There we go. So 7/45 6/7 is that limit as t gets closer to 5. And that's it for that one. Let's take a look at what happens when we take the limit as t gets closer to 4. Well, we're going to do the exact same thing, but this time we're going to let t go to 4. Instead of letting t go to 5. Now, in this case, it's pretty straightforward because when we are at 4 on each of these individual expressions, the t squared minus 3t minus 10 over 5, t minus 5, the t squared plus 4t, and the 6 over t plus 2. When t goes to 4, I can just simply plug that in. Those expressions give me continuous functions in 2 dimensions. So all I have to do is plug that in. Whoops, let me get rid of all that. So when you plug in 4 in for t, we get 4 squared minus 3 times 4 minus 10 divided by 4 minus 5. So I got a positive 6 in my x component. Again, hopefully we don't need to do that. I'm just by hand, I'm just replacing every t with the number 4. And then the same thing goes here. When I replace t by 4, I get 4 squared plus 4 times 4, which is 32. So my second component is going to be a 32. And then my third component is going to be 6 over 4 plus 2, which is 6 over 6, which is 1. So the limit of r of t as t goes to 4 is 6, 32, 1. Now, I'm sure you've gotten the idea, but I'm going to do a couple more. Well, for many reasons, but for one of many reasons, we are going to take a look at this example. So let's say limit as r of t as limit of r of t as t goes to -2. So instead of going to 5, we're going to -2. Now, if I do the same thing I did earlier, I can simply plug in -2 into the first and second components, into what we would call the y and the x components. So if I plug in -2, since this is a continuous function at -2, I can just plug it in. There's no problem. I'd say -2 squared. Make sure the negative goes inside of the parentheses. -3 times -2 minus 10 gives me 0. Divided by -7 would give me 0 still. Again, make sure when you plug this in, you plug it in inside of parentheses. I'm doing a little bit of a my notation is not perfect on this, but if I eliminate the limit just by plugging this in, I basically get 0 over -7, which gives me a 0 in the x component. If I plug in -2 here, again, make sure you plug it in inside of parentheses. What we get, -2 squared plus 4 times -2 gives you a -4. So in the y component, you get -4. I'm going to eliminate this real quick. I think we get the idea. And then I have this last piece. Limit as t goes to -2 of 6 over t plus 2. It turns out that as you approach -2 from one side, from the right, you're going to go out to positive infinity. If you approach from -2 from the left, you're going to go down to negative infinity. And therefore, this limit here does not exist. One side shoots off to infinity, the other side shoots off to negative infinity. So this limit does not exist. Now, notice the first two parts did exist, but the third part did not exist. And so what we say about this entire thing, the limit of the entire vector valued function, we say the entire limit does not exist. And generally the shorthand for that is DNE. So if we get one part that doesn't exist, then that means the limit does not exist. Now that's not going to be a problem on the next example. The next example is another one where we're asked to plug in a number, or excuse me, we're asked to use a number which we can plug in into all of our component functions. So basically, you can simply plug this in. If you plug in 0, you eventually get negative 10 over negative 5, which is a positive 2. If I plug in to this y component, I get a 0. And if I plug in to the z component, I get a 3. So because we have continuous functions in the real numbers, the t squared plus 4t, this expression is continuous at 0 in the real numbers. This expression is continuous at 0 in the real numbers. We can just plug in t equals 0. That's the nice thing about having continuous functions in the real numbers. Now, another thing I want to point out before I move on is that sometimes you may have quantities in here that match up. Like you might have a 6, 32, 1. There might be some other function out there that gives you a 6 for your x component. Again, that does not mean that those things are the same, right? So remember, a vector is only the same as another vector if all 3 components are equal. And it is possible in certain cases to get a specific number in, let's say, the y component in multiple ways and get different x and z components but have the same y component. That's probably more complicated than it really needs to be. Basically, it's just saying, remember, vectors aren't equal unless every component of the vector is equal. Since we've done limits and I've mentioned continuity of real functions, let's talk about a continuous vector valued function. So we say that a vector valued function defined on an open interval containing C is continuous at C if the limit of the vector valued function as t approaches C gives you the same thing as the vector valued function when you input C. This is very, very similar to continuous real valued functions, except now we have vectors involved. And we say a vector valued function is continuous on an interval if it's continuous at every value in that interval. So in other words, our vector valued function is continuous at C if each component function, those real valued functions, is continuous at C. So if every single component function is continuous, then the vector valued function is continuous. Because remember, we know how to plug in a value. We just plug it into the 3 component forms if we're in R3. We know how to take a limit. We just apply the limit to the 3 component forms. So being equal means that all 3 of those things are equal. So let's use our previous work and decide if this vector valued function is continuous at 5, if it's continuous at 4, if it's continuous at -2, and if it's continuous at 0. This is the same example, the same function we had in our last example. So let's check this one out and check for continuity at those values. So you'll have to apologize. I'm going to leave up the work that I've done previously and just add on to it. So hopefully that's fine. If you want to rewrite some things, you can just rewrite the limit. I'm not sure why that capitalized, but usually we have lowercase. So we know for this first one, let's say we want to find if we're determining continuity. So we're determining continuity at t value of 5. So we know that the limit exists and that that limit is 745 6/7. So now what we're going to do is we're going to plug in 5 and see what we get. So simply plug in 5 and notice what's going to happen on that first component. We're going to be dividing by 0, and therefore this first component does not exist. By the way, it's perfectly fine to just plug in 5 in the second component, and in the third component, in the second and third component, we're going to get 45 and then 6/7 when I simplify. But that means this R of 5 does not exist. Since it doesn't exist in one component, overall it doesn't exist. And so it did have a limit of 7 in the x component. However, when you plug in 5, it did not exist. That means that this function is not continuous at 5. So that's all we're doing. So not continuous at 5 because this was not equal to that. Let's check out 4, and I'm going to give myself a little bit of space. We're going to deal with a t value of 4. All right, we already found the limit, and so now all we have to do is figure out r of t. What happens when I plug in the number 4? Well, I'm going to plug in the number 4. I'll just simplify as we're sitting here. I might as well simplify in one big step. Obviously, if I was taking notes, I'd probably write down multiple steps here. But plug in 4. And 4 squared minus 3 times 4 minus 10. That's 16 minus 12 minus 10, which gives you a negative 6. Again, I'd be putting multiple steps if I was writing this down on a piece of paper. 4 minus 5 is a negative 1. So I get a 6 when I plug in 4 for my x component. 4 squared plus 4 times 4, that's 16 plus 16, that's 32. And then 6 over 4 plus 2, so that's 6 over 6, that's a 1. So when I plug in 4, it gives me the same as what I get by taking the limit as t goes to 4. Therefore, this one is continuous. At t value of 4. Let's take a look at this one. Well, as t goes to negative 2, we already know that the limit does not exist. So I don't even really need to plug in anything. I don't need to go back and take my vector valued function and plug it in because I already know that the limit does not exist. And if the limit does not exist, then it cannot equal r of -2. Therefore, this function is not continuous at t value of -2. And then lastly, we'd plug in 0 into my vector valued function. When I do that, for my x component, I get, well, lots of zeros. Keep doing that. But essentially, the numerator becomes -10, the denominator becomes -5, and -10 over -5 is a 2. Zero squared plus 4 times 0 is just 0. 6 over 0 plus 2, that's 6 over 2, which is 3. So my function has limit as t goes to 0, which is the same as r of 0. Therefore, this is continuous at t value of 0. So my limit and my function value match up, so it's continuous. When my limit doesn't exist, it can't match up with my function value, so I get not continuous. Here, my limit and my function value matched up again, so I had continuous. Here, my limit existed, but my function value did not, so we get not continuous. So that's how we determine continuity using the idea of limits. Limits just get applied to each component in the vector. Now, in terms of derivatives of vector valued functions, derivatives is the next thing we usually learn in calculus. So let's talk about derivatives of vector valued functions. Now, by definition, the derivative of the vector valued function at c is the limit as h goes to 0 of our vector valued function when you plug in c plus h minus our vector valued function when you plug in c, and all of that is divided by h. So this is our normal definition of limit. Notice that it uses a limit as h goes to 0. That limit, well, let me go and restate this. When you actually go through here, when you subtract vector valued functions, you subtract them on their components. If we divided by h, we could divide each component by h. And then when we take a limit as h goes to 0, we can take the limit of each component as h goes to 0. In other words, when we find the derivative, we're going to do so on the individual components of our vector valued function. So here's what I mean. In general, the derivative of a vector valued function is the derivative of the x component, comma, the derivative of the y component, comma, the derivative of the z component. So it's f prime, g prime, h prime, where those are the x, y, and z components. So we just apply the derivative to each piece of the vector valued function. And that gives us the derivative. That all comes out of the algebra of how vectors work in this definition. You subtract vectors, you subtract them component-wise. You can divide by the scalar h, so you divide each component by h. And then you apply the limit. Well, you apply the limit to each of the components. And we get this. And so this is really the thing to know. Now, if you think about what the derivative is telling you, derivative should tell you a direction. And it's telling you the direction of the tangent line. So if we're in, let's say, 3 dimensions, we're getting a direction of the tangent line in 3 dimensions. So our line needs to be a line in 3 dimensions. And we can find that tangent line by knowing the direction and a point it goes through. So if I know the direction of the tangent line is given to me by the derivative of r, then that's going to be my direction vector. If we're saying what point does it go through, well, it goes through r of whatever point we're at. So if I'm talking about a t value, which is equal to the number c, I do r of c plus t, that's variable t, times r prime at c. So we get a tangent line from our derivative. In a very similar way, we would get a tangent line from the derivative of a function in 2 variables. So let's take a look at this function. We have the vector valued function, which is vector 5t squared plus t, comma 2t minus 1, comma t. And we want to find the tangent line for that vector valued function at t value of 1. We'll do this algebraically and see how it looks graphically as well after we do it algebraically. So in order to do the tangent line, we first need to find the derivative of r. And if we're going to find the derivative of r, all we have to do is take the derivative of each of these components. Now the variable is t, so we're taking the derivative with respect to t. So 5t squared plus t is going to turn into, let me just delete all that. So 5t squared plus t turns into 10t plus 1. 2t minus 1, the derivative is going to be 2. And the derivative of t is simply going to be 1. So that's the derivative of r of t. So the derivative function is another vector valued function with these inputs. Now, at t of 1, which we were asked to evaluate, well, these two functions, both r of t and r prime of t, can just be plugged in. Let me rephrase that. So if I want to, let's do r of 1, plug in 1. I'm going to get 5 plus 1, I'm going to get 6 here. 2 times 1 minus 1 gives me a 1. And then plug in 1 there, I get a 1. So I get 6, 1, 1 when I plug in 1 into my r. If I take the derivative, I'm not plugging in 1 to the actual function. I'm plugging in 1 into the derivative function here. So I'm going to plug in 1 into this function here, and I'm going to say 10 times 1 plus 1 gives me an 11. And then no matter what I plug in, my y component is a 2, my z component is a 1. So I get 611 for when I plug in 1 into the function, and I get 1121 when I plug in 1 into the derivative. And so that means that my line, my tangent line at 1, let's properly write that. So my line is going to be, I can write this in numerous ways. I'm going to write it as a single expression. It's going to be this plus t times this. So 6 plus 11t for my first component, 1 plus 2t for my second component, and 1 plus 1t for my third component. If you want to write that as a sum of 2 vectors instead of as a single vector, by all means go ahead. Doesn't matter how you do that. But that is the tangent line at t equals 1. Notice that we are not plugging anything in because I need to write this as a line. So that's the line. All right, so here's our graph of 5t squared plus t, comma, 2t minus 1, comma t. Notice that that's this smooth curve in 3-dimensional space, which we expected with the vector valued function. Kind of looks like a parabola on its side. Now, if we're talking about the point where t is 1 gets us to point 611. So if you're looking down on it, looks like 6 in the x direction, 1 in the y direction. And then if you're looking at, it looks like 1 up in the z direction. So it's that point there. Obviously, in this graphing system of Desmos, makes it a really big point so you can see it. Now the tangent line is 6 plus 11t, 1 plus 2t, and 1 plus 1t. And if you think about this, this needs to be a line that in 3-dimensional space is going in the same direction as our curve at that point. So if you can see it, if you're looking down, this tangent line goes through, hits that point, and just keeps going. Might be easier to see without that point. So looks like that. And that's no matter which way you look at this. No matter which way you look at that, notice this tangent line is going in that same direction when you hit that particular point. This particular point here of 611, same direction. If I scroll out a little bit, you can see that it just barely hits the curve in 3 dimensions and then shoots off. But that's my tangent line. So it does the same thing like you probably saw what a tangent line does in a previous calc course. Let's do another. Let's find the derivative of this vector valued function. And then let's try to find the tangent line at t of pi over 3. So obviously we're using radians here. Our vector valued function is 2 cosine t, comma 3 sine t, comma t. So let's find the derivative of this and then find the tangent line when t is pi over 3. All right, so vector valued function of 2 cosine t, comma 3 sine t, comma t. Let's first take the derivative. If I take the derivative of sine, if I take the derivative of sine, I get a cosine. If I take the derivative of cosine, I get negative sine. So I get negative 2 sine of t as my first component. If I take the derivative of 3 sine of t, I get 3 times cosine of t as my second component. And then the derivative of t is 1. So r prime of t is negative 2 sine of t, 3 cosine of t, 1. Now at t of pi over 3, I would just plug in pi over 3 into my r value. Now cosine of pi over 3 is 1/2. So I get 2 times a half when I plug in pi over 3. Sine of pi over 3 is root 3 over 2. And then when I plug in pi over 3 for my z value, I get pi over 3. By the way, 2 times 1/2 is just 1. 3 root 3 over 2. We'll get an approximate answer when we go to graph that, but I'll leave it as exact right now. And then pi over 3, again, that's just a little bit over 1. We can get a decimal version if you want, but I'll just leave it as exact right now. In a similar way, if I take the derivative of r and I plug in pi over 3 into that, well, remember sine gives me root 3 over 2 when I plug in pi over 3. So I get negative 2 times square root of 3 divided by 2. That's my x value. Cosine gives me 1/2 when I plug in pi over 3. So I get 3 times 1/2. And then when I plug in pi over 3, my z value just stays as a 1. Let me simplify this a little bit. 2 over 2 here is going to cancel. I'll just be left with the square root of 3. So I get negative square root of 3 for my x component. 3 times 1/2 is 3 over 2 as my y component, and 1 as my z component. If I want to find the line that is tangent to my graph when t is pi over 3, I'm going to take this as my fixed point, 1, 3 root 3 over 2, comma, pi over 3, and this as my tangent vector, negative root 3 3/2, 1. So it's a little bit messy, but it's not crazy. 1 minus t times the square root of 3. That's my x component. 3 square root of 3 over 2. That's my fixed part of y. And then I have to do plus t times 3/2, or 3/2 times t. It doesn't matter which way you put it. And then pi over 3 plus 1t as my z component. Again, a little bit messy. You could put everything and round everything to 2 decimals if you like, or you can just keep it like that. Let's look at and see how this looks. All of this put together on a graph. All right, so this is one of those graphs that looks spirally. If you look straight down along the z-axis, it looks like an ellipse, but it kind of looks spring. It's like a spiral wrapped around the z-axis. And again, if you look straight down that z-axis, it looks like an ellipse. Now, the point that we're looking at is when t is pi over 3. And when t is pi over 3, we're at this point here. Let me try to... So my tangent line should go through this point and in the same direction as my graph. So it should be shooting up a little bit and in this way. And sure enough, when I graph that, it looks like we think it should. Goes through that point and it's tangent to the graph, just touches that graph at that single point and then comes back through. That might be the best angle. So that is how we can figure out derivatives and tangent lines at a specific point. Obviously, any sort of graphical shape, you can do that as long as we get smoothness of the curve. Just like when you're dealing with functions, if you don't have continuous functions, they're not going to have nice derivatives. If I don't have continuous, smooth, vector valued functions, I'm not going to have derivatives. So if there were any sharp corners or discontinuities in my graph, I wouldn't have a derivative at that point. But as long as I have smooth curves in three-dimensional space, then I'm going to be able to get these derivatives. Now let's take a look at some properties of derivatives. Let's let R and S be differentiable vector valued functions, so ones that have derivatives, and let C be any real number. Well, the derivative of the sum of two functions is going to be the derivative of the first function plus the derivative of the second function. This works just like our derivative rule of adding two functions in the real numbers. So it's analogous here. If you take a derivative of the sum, it's the same thing as the sum of the derivatives. The same is true for scalar multiplication. If I take some scalar times my vector valued function and then take the derivative, it's going to be the same as taking the scalar times the derivative of the function. So that means the derivative operator, again, this is all derivative with respect to t, because t is my variable here. The derivative operator distributes over addition, and it goes through scalar multiplication. Now, if you remember, these are basic rules we have on functions. These are our basic derivative rules on functions for real numbers. Another derivative rule that we had with functions on real numbers was our product rule. Now, this is going to be an interesting thing because when we have a vector valued function, we can take three different kinds of products. We can take scalar multiplication products, we can take dot products, and we can take cross products. It turns out if we're doing any of those three products, then the product rule of derivatives will work as long as I keep the type of product the same. So again, let's let R of t and S of t be differentiable vector valued functions. And let's let f of t be a real valued function. That's one where I plug in a t and I get out some real number. If I take a real number valued function and multiply it times a vector valued function, then this would distribute like scalar multiplication. You take the f of t, you'd multiply times the x component, times the y component, times the z component. Well, if you take a derivative of the product of f and r, the product rule says take f prime times r, that is normal r, plus normal f times the derivative of r. Similarly, if I have the dot product of two functions, r and s, and then I take the derivative of the dot product, I'm going to take the derivative, that would be equal to the derivative of r dot product with s plus normal r dot product with s prime, or the derivative of s. And then lastly, cross product. If I take the derivative of the cross product of r and s, I can also do derivative of r cross product with normal s plus normal r cross product with derivative of s. By the way, notice that order matters on this one. So when I dealt with the r, I always kept it on the left-hand side when I'm dealing with this cross product. So both the r prime and the r are on the left-hand side. Order matters there. Now, the last property of derivatives that we're going to look at and deal with is the chain rule. Now, it's going to work a little bit different because we have a vector valued function. So our input needs to be something that gives out a real number. So when we deal with a chain rule, we want a vector valued function, and then inside of that, we're going to put f of t, a real valued function. If I take the derivative of r of f of t, I'm going to take the derivative of r, plug in f of t, and then I have to multiply times the derivative of the inside function. So I have to multiply by f prime of t. Notice this is going to be a vector, and then I'm going to be multiplying by f prime of t, which is going to be a real number valued function. Just to think through this dot product, when I do dot products, I get real numbers or real functions. So you're getting essentially a real number when you do the dot product derivative. When you do a cross product derivative, since cross products of vectors in 3 dimensions give me outputs that are vectors in 3 dimensions, my output is going to be a vector in 3 dimensions. Same thing up here. We got vectors in 3 dimensions times scalars, essentially. Vectors in 3 dimensions times scalars, we're adding them up. This one you can do in 3 dimensions or 2 dimensions. This one you can do in 3 dimensions or 2 dimensions. When you do the cross product, you need to be in R3 to get things to work out. Dot product or scalar multiplication you can do in 2 dimensions if you like, or any other dimensions if you like. But the cross product, you need to be in 3 dimensions for things to work out. All right, so let's take the 2 functions we just dealt with. I'll call the first function we dealt with R, and I'll call the second function we dealt with S. And let's take the derivative with respect to t of R plus S. Let's take the derivative with respect to t of the dot product of R and S. And then let's take the derivative with respect to t of the cross product of R and S. Once we do that, so that I don't have to go back to this slide, once we do that, let's take that same R and let's have real valued function f of t be 4t minus 3. And let's calculate the derivative of the product of f of t and r of t, f of t times r of t, and the derivative of r of f of t. So that's the composition of R with f of t. So we'll do all of those things, and then we'll turn back to our notes. All right, so we have our R and our S like we had before. Since we've already taken the derivatives of those, I think I will utilize that. What do I have here? There we go. All right, so I will utilize that. I'll utilize what we've done before. So when you add two functions and then take the derivative, you should be able to take the derivative of the first function, which earlier we found was 10t plus 1 to 1, plus derivative of the second function, which earlier we found was negative 2 sine of t, 3 cosine of t, 1. Adding those things up, we just get the components added up. So 10t plus 1 minus 2 times the sine of t. That's my x component. My y component is 2 plus 3 times cosine of t. And my z component is 1 plus 1 or 2. So when we add those two things up, this, and then take the derivative, this is what we get. Now you could have also added them by hand and then taken the derivative, but since we already took the derivative of each one individually, that was nice to do. Same thing is true with the dot product and cross product. Now you have to watch out for this. Remember, when you do a dot product, I'm going to shorthand this. You can do, it doesn't matter if you do normal R times S prime first, or if you do R prime times S, but we're going to get R S prime plus R prime times S, essentially. Now I know I didn't write the little arrow above the R and the S's, but that's what we're getting. And so if you go and you stick in normal R, that's normal R, dot product, whoops, dot product with S prime. Now this was our S prime. I'll use another line here just a moment. Plus R prime, the derivative of R was this, dot product with normal S, which is this, we're gonna get, well, we're gonna get a lot of stuff. We're gonna get 5t squared plus t times negative 2 sine of t. Plus 2t minus 1 times 3 cosine of t. Plus t times 1. And then I'm going to add that to 10t plus 1 times 2 cosine of t. Not the nicest thing to multiply, but that's okay. 2 times 3 sine of t plus 1 times t. Now you can, if you'd like, combine like terms and do all kinds of distribution and combining like terms. For instance, if I take negative 2 times sine of t times 5t squared plus t, I can take the negative 2 and multiply it times the two terms over there. So we'd get negative 10t squared minus 2t all times sine of t. And then I can do the same thing with cosine. I can take the 3 as a coefficient and distribute it left. I can do the same thing with this cosine, take the 2 as a coefficient and distribute it to the polynomial in the left. And get something like this. And then I can combine, since this has a sine t and this has a sine t, I can combine the coefficients. I can combine negative 10 t squared minus 2t plus 6 and put all of that in front of a sine t. I can do the same thing with cosine. With cosine, I get 6t minus 3 in front of this cosine, and 20t plus 2 in front of this cosine. So 20t plus 6t is 26t. Minus 3 plus 2 is a minus 1. And that's the coefficient of cosine. And then 1t plus another 1t gives me 2t. And so that's what I get out when I do the dot product and then take the derivative. And that would be my final answer. Again, it was kind of messy there in the middle because there was a lot of dot product stuff going on. Maybe it's easier to see this way, but that's what's happening. A lot of simplification going on. Hopefully that makes sense. Maybe it's easier to see that way. Now, cross product works in a very, very similar way. We're going to end up taking R times S prime plus R prime times S, where the multiplication we're doing is a cross product multiplication. Now, in this case, with these particular functions, I don't know if it's easier to do the cross product and then try to take a derivative or do the derivatives and cross products. Not exactly sure, but what I'm going to do is I'm going to do it I'm going to, since I've already taken the derivative of S, the derivative of R, I'm going to do it this way. So let's take exactly what we did here, except exchange our dot product for a cross product. R cross product with S prime plus R prime cross product with S. Now it's going to take some time to do the cross product. That's okay. Not the end of the world, but it'll take some time. So let's remember how to do cross product. When we cross product, we're going to take uh-oh. Do that right? There we go. We're going to take a 3x3 matrix and take the determinants of that. Specifically, we'll do the I, J, K. I'm leaving off the arrows on the top. Here, we would do, so I'm going to do the cross product first. Let me say, of R cross product S prime. So R cross product S prime would be 5 T squared plus T, 2T minus 1, and then T cross producted with negative 2 sine of T, 3 times cosine of T, and a 1. What kind of vector are we going to get when we do that? Well, we're going to get a vector that's really messy. In fact, let me write it here because I know it's going to be really long. All right, coefficient of I, which is going to be our x component, is going to be found by eliminating first row and then the first column, and then we're left with a 4x4 2t minus 1 times 1 minus 3 cosine t times t. So that's the x component. My y component, whoops, is going to be negative of whatever I get. I'm going to do the 2x2 thing. I'm going to eliminate the j, eliminate the ik, j row, j column, j row, j column. So I take 5t squared plus t times 1. And then I'll do a minus negative 2 sine t times t. So that's a lot of minuses. So minus negative 2 times t times sine of t. Minus a negative becomes a positive, obviously. Don't forget there's a negative out front. So if you really wanted to, you could distribute that in. A lot of negatives here. And that is your y component. And then your z component, you're going to take 5t squared plus t times 3 cosine of t. That's going to be a mess. So we're getting 15t squared plus 3t times cosine minus negative 2 sine t times 2t minus 1. So minus negative 2. Let's take 4t minus 2. That's what you get when you multiply 2 by 2t minus 1. And then that's in front of sine. Subtracting a negative gives you a positive. Let's see if we can make that a little bit smaller so that it can fit on one line. Now we'll see. There we go. So now it fits on one line. Whew, that is one big ugly mess, but that's okay. That's just, by the way, our first cross product. Now we're going to have to add that to our second cross product, which we can get it's going to be hard. Let's put it on one page. It's going to be hard to get on that page. So, all right. So our second cross product, let's do second cross product as 10t plus 1 to 1. 10t plus 1 to 1, cross producted with 2 cosine of t, 3 sine of t, and t. All right. So again, coefficient of the I, which is going to be our x component, we're going to do 2t minus 3 sine times 1. So 2t minus 3 sine of t. My y component. I cancel out the column and row j is in. So I'm going to get, don't forget to do the negative of this whole thing. 10t plus 1 times t. So that's 10t squared plus t minus 2 cosine t times 1. If I distribute that negative, I end up with negative 10t squared minus t plus 2 cosine t. And then my z component, again, cancel out the column of k and the row of k. We're going to get 10t plus 1 times 3 sine t. I'm going to write that as 30t plus 3 quantity times sine of t minus 2 cosine t times 2. That's minus 4 cosine of t. Now remember, I've done this cross product and I've done this cross product. The goal was to find the derivative of the cross product of R and S. If I want to find that, then what I have to do is I have to add those two things up. So I need to add these two vectors up. I need to add this cross product with this cross product. And it is not going to be an easy thing, but we can add it pretty easy. Add the x components. So we do 2t minus 1 minus 3t cosine t. Add that to 2t minus 3 sine t. The 2t and 2t are going to add to 4t. I'm going to get a minus 1. We get a minus 3t times cosine of t. And then I'm going to get another minus 3 sine of t. That's all just my x component. Now my y component, I have minus 5t squared minus t minus 2t sine t plus a negative 10t squared minus t plus 2 cosine t. Again, combining like terms, we're going to get minus 15t squared minus 2t minus 2t sine of t plus 2 times cosine of t. And then lastly, I'll do my z component, which is going to be this z component plus this z component. This one we have kind of we have something in front of cosine, something in front of sine. We can combine like terms there. So let's do the cosines first. 15t squared plus 3t minus 4. Let's see if I can do this the way I want it to. Ah, there we go. Now that doesn't look very good. When these things get really long, it's no, they're not going to look good. So 15t squared plus 3t minus 4, all in front of a cosine of t, plus the coefficients of sine here plus the coefficients of sine here add to 34t plus 1. All is the coefficient in front of sine of t. So the derivative of the cross product becomes this really messy looking vector. Again, it's doable. It takes me a long time just because cross product takes me a long time. And it turns out that the functions that I had, there wasn't a lot of good simplification that could go on midway through the process. So this one was really long. It hopefully, if you come across one where it has you do a cross product, then in the derivatives, hopefully they're a little bit nicer functions to deal with, and they simplify a little bit nicer. Now, on the next slide, we were asked to calculate f of t times r of t, the derivative of that quantity. And just like before, we go f prime times normal r plus normal f times r prime. But this time, the multiplication we're dealing with is simply function multiplication, or I should say scalar multiplication, essentially. So f prime, the derivative of f is the derivative of 4t minus 3. That's just 4. R is our normal r. So we're taking 5t squared plus t, comma, 2t minus 1, comma, t. So that's f prime times r. Then I'm going to take f times r prime. Now f is 4t minus 3. And I'm going to multiply that times r prime. R prime is going to be 10t plus 1, comma, 2, comma, 1. We've already done that. Okay. So in the first case, when you distribute the 4 times 5t squared plus t is going to be 20t squared plus 4t. Four times 2t minus 1 is 8t minus 4. And then 4 times t is just 4t. In the next component, or in the next part, we have to be a little bit careful because we're taking the 4t minus 3 and we're taking that entire polynomial times the 10t plus 1. So that's going to give you 40t squared plus 4t minus 30t minus 3 when that's all multiplied out. Now I'm also going to combine these like terms of 4t minus 30t and come up with a minus 26t. And that's my x component. Then when I take 4t minus 3 and I multiply it by 2, I end up with 8t minus 6. And when I take 4t minus 3 and multiply it by 1, I end up with 4t minus 3. Now adding, well, when we add these two things together, we add the x components together. So 20t squared plus 40t squared is 60t squared. 4t minus 26t is minus 22t. and then minus 3. That's my x component. My y component, when I add these things together, we get 16t, 8 plus 8 is 16, so 16t minus 10. And my z component is 4t plus 4t minus 3. That's 8t minus 3. So that one's much, much easier to deal with. So this is real valued function multiplied times vector valued function. Take the derivative of that. Lastly, we're going to take the derivative of the composition of R and F. Now, this is a little bit tricky. I'm not going to go through every little detail, but we're taking the derivative with respect to t of this thing where I've replaced each t with a 4t minus 3, the f part. So I replace each t with 4t minus 3. Replace this t with 4t minus 3. Now in this example, it's probably doable by hand to actually go through all of this and take the derivative after I do it. But in other examples, it would be harder. So instead of working through and doing polynomial multiplication and simplification, what we're going to do is we're going to take R prime, plug in f of t, and then multiply by f prime of t, multiply by the derivative. So in other words, a lot of people will just say R prime of f multiplied by f prime. So that's the way we're going to do it. Now, if you remember what R prime was, R prime, well, let's go back up here. There's my R. So my R prime was 10t plus 1, 2, 1. So that's my R prime. If I want to plug in f of t, that means I replace every t I see with 4t minus 3. And then after I do that, I multiply by my f prime. Remember, f was 4t minus 3, so f prime is simply 4. Notice that trying to take a derivative of this messy looking polynomial stuff is going to be more difficult in general than doing this. So what we end up with is a 40t minus 30, comma, 2, comma, 1, all multiplied by the scalar 4. That's 160t minus 120, comma, 8, comma, 4. So the chain rule gives me this as the derivative. Hopefully I did all of my calculations right. Obviously, there's a lot of calculations to do in some of these. And we hope that we get nice functions to deal with and things start canceling out and simplifying as we go through so that you don't have to do as much computation as we did like on this one. This one was a ton of computation. Most of them don't turn out that way. All right. So we've seen some examples where we can take derivatives using the chain rule, where we can use a product rule between a real valued function and a vector valued function, where we can do product rule with cross products, where we can do our product rule with dot products, where we can do a sum. Obviously, scalar multiplication we could do if we wanted to. We did that within some of the problems from earlier, but a lot of different derivative property examples. And since now we've done derivatives, let's jump to antiderivatives. An antiderivative of the vector valued function r of t is a function capital R of t such that the derivative of capital R is equal to r. In other words, the antiderivative is a function whose derivative is my given function. Hopefully we know that in order to get an antiderivative, there's a whole class of antiderivatives. And the way we get the class of antiderivatives is by doing the indefinite integral. So if we want to integrate a vector valued function with respect to t, just like what you would think, we would integrate each component of my vector valued function. So integrate f and put that into the x component, integrate g, put that into the y component, integrate h, put that into the z component. So antiderivatives work the way you would think. Now that is an indefinite integral. If you do a definite integral on a continuous vector valued function, it needs to be continuous or else it doesn't make sense. Then the definite integral from a to b of our vector valued function is just going to be the definite integral from a to b of the x component, the definite integral of the y component, definite integral of the z component. So we can just integrate the x component, integrate the y component, integrate the z component separately, evaluate those from a to b. So let's look at an example. We're going to take our polynomial function, vector valued function, r of t once again, 5t squared plus t, comma, 2t minus 1, comma, t. We're going to find the antiderivative or the indefinite integral, and then we're going to find a specific antiderivative such that when you plug in 0 for t, you get the vector 0, 4, 2. So let's take a look at this. So if we want to find the indefinite integral of r of t with respect to t, we're going to integrate each of these individual pieces. Now I'm going to do that. They're pretty straightforward to integrate. So we're going to integrate 5t squared plus t. We get 5/3 t to the third plus 1/2 t squared plus some constant. Now I'm going to call this constant sub x because that constant is going to be the constant that I find in my x component. Then we're going to do the same thing to y. We're going to take the antiderivative of 2t minus 1. That's going to be t squared minus t plus constant with respect to y. Maybe I'll write these as lowercase constants. And then lastly, the antiderivative of t is 1/2 t squared. Now we're going to have to add a constant this time, a constant in the z part. And so that's my new vector valued function. And if I throw in any constant in the x component, and then in the y component, and then in the z component, I'm going to get some antiderivative. Now, this is r of t. So this is the r we're talking about. Which is capital R of t. So it's that vector. Knowing that r of 0 is 0, 4, 2 tells me that if I take 0, 4, 2, it will equal what happens when I plug in 0 into this vector valued function. So I'm going to plug in 0 into every t I can see. And then obviously we can simplify. We're going to end up with zero, 4, 2 equaling my constant in the x component, my constant in the y component, and then my constant in the z component. So Cx, Cy, Cz are 0, 4, and 2 respectively. And that means if I go back up here, the specific antiderivative that I wanted was 5/3 t to the third plus 1/2 t squared plus 0. That's my constant in the x part, comma, t squared minus t plus 4, comma, 1/2 t squared plus 2. So that's the specific antiderivative that I wanted. Notice that when you're dealing with constants, you can get a constant in each of the components, and they don't always have to be the same as we see here. Here we have 1 is 0, 1 is 4, 1 is 2. So those constants in the component pieces could be different. Let's do a similar thing to this. Let's find the antiderivative. Let's find the indefinite integral, first off, of this vector valued function, and then try to look for the specific antiderivative where r of 0 is 1, -1, 3. See if we can do that. Okay, so first let's integrate our function. And to do an integration of the function, I do integration of the components. So I integrate 2 cosine of t. The antiderivative of 2 cosine of t is 2 times sine of t. That is positive 2 sine of t when I take the antiderivative. When I take the antiderivative of 3 sine of t, I end up with -3 times cosine of t. And when I take the antiderivative of t, I get t squared divided by 2. So think of that as coefficient 1/2. Now, one thing I left off of here is the constants. So I wanted to add the constant with respect to x in the x component, the constant with respect to y in the y component, and the constant with respect to z in the z component. So that is the antiderivative. I'll flash in there. Or I should say the class of antiderivatives, because any 3 constant numbers, any 3 real numbers we choose to plug in there will give me a different antiderivative. But the class of all antiderivatives will be of this, will be that, okay? And so it says, let's find the specific antiderivative where when you plug in 0, you get 1, -1, 3. Well, all I'm going to do is I'm going to take my r. I'll do it slightly different this time. I'll do my r of 0 on the left-hand side. And then I will do my 1, -1, 3 on the right-hand side. Plugging in 0 here. Everywhere we have a t. On the left, be careful about this because on the left, we have a vector, but remember, sine of 0 is 0. Cosine of 0, on the other hand, is 1. So on the left, I get 0 plus c sub x, constant in the x component, -3 times 1 plus constant in the y component, and then constant in the z component. So be very careful about that middle term, because that middle term, it's not just c sub z, it's -3 plus c sub z. And we know that has to be 1, -1, 3. Now, what's that mean? That means my c sub x is 1. My c sub y is actually a 2. And my c sub z is a 3. So the actual antiderivative that we were looking for, again, remember indefinite integral, the indefinite integral gives me the class of antiderivatives. The indefinite integral that the antiderivative that I was looking for was the one where c of x was 1, c of y is 2, and c of z is 3. So that would be my vector valued function that has r of t as the derivative and which goes through 1, negative 1, 3 when t is 0. Just to hit home the value once again, the indefinite integral gives me the class of antiderivatives. I've been writing it like this. Someone else may write it slightly different. Someone else may write it as a sum of two vectors, like 2 sine of t, negative 3 times cosine of t, and then 1/2 t squared. And then they'd say, well, plus a constant vector. And sometimes people will write a constant vector as c sub x, comma, c sub y, comma, c sub z, like I just did. Or another way to write a constant vector is to write a vector with capital C as the constant. So this is a constant vector. So that's another way to write that as well. I don't care which one you write it. That is the way. Again, two different ways you can write it. But remember, these constants in the components could be different. And if we have this specific value, well, then we can find the specific antiderivative. Let's do an example of a definite integral. Let's integrate r of t from 2 to 5, where r of t is the vector valued function 5t squared plus t, 2t minus 1, and t. So I'm going to go ahead and do this, and I'll show you how I write it, but there's a bunch of different ways to write it, a bunch of different ways to do the notation. Now, we've already done the indefinite integral already, and now we're just going to take the definite integral. If you remember about doing a definite integral, we know how to integrate these individual functions. So when you do the definite integral, it's going to be just like that. We're going to integrate from 2 to 5. And so we're going to integrate from 2 to 5 with respect to t, each of these individual functions. Now, again, different notation. Some people like certain notation. Some people like other notation. I'm not a stickler for which notation you like the best. Which notation you like the best is fine with me. If you want to, you can do 5/3, let's say t to the third plus 1/2 t squared. And that's the antiderivative. And then what we do is we go from 2 up to 5, and that'll become my new x value. I like this notation where it's in square brackets, and then after I integrate, I put the 2 to 5 from the left-hand side to the right-hand side. By the way, you'll notice I don't put any plus constant here because it's not needed. If you plug in 2 and if you plug in 5, we're going to subtract those, and that's going to cancel out this constant. So I can assume that the constant is 0 in each one of these if I'm doing a definite integral. It's not going to change anything. In the second component, we get t squared minus t. Again, we're going to plug in 2, plug in 5, see what happens. And in the third component, the z component, I get 1/2 t squared. Again, plug in 2, plug in 5, look at the difference. Again, there's multiple ways of writing this. Some people write it all in one. Some people write 2 vectors and then subtract. They'll plug in 5 and get a vector, and then plug in 2 and get another vector and then subtract. That's perfectly fine. I kind of like that. I'll do the first vector. What's going to happen when I plug in 5? Well, 5/3 times 5 to the third power plus 1/2 times 5 squared becomes 220 and 5/6. That's my x component. When I plug in 5 here, I get 25 minus 5, so I get a 20. And when I plug in 5 here, I get 1/2 of 25, which is 12.5 or 12.5. I'll just write 12.5. And then I subtract off what I get when I plug in 2. So if I plug in 2 here, 5/3 times 2 to the third plus 1/2 times 2 squared is 15 1/3. When I plug in 2 here, I get 2 squared minus 2, which is 2. 4 minus 2 is 2. And then if I plug in 2 here, 1/2 times 2 squared, that's 1/2 of 4, also 2. So that's one option for how to write the notation here. When you subtract, if I take 220 and 5/6 and I subtract 15 1/3, I get 205.5. I'll just write 205.5. Oops, thought I wrote that in a vector scenario. 205.5. 20 minus 2 is 18. 12.5 minus 2 is 10.5. So that is one option for writing my vector for the notation. Some people like that. It's basically I plug in the 5 into all 3 components, get a vector, and then plug in the 2 into all 3 components, get another vector, and subtract. Other people would not like that. Other people may use notation in which you plug in the 5 and then you subtract what happens when you plug in the 2 in the x component. So they plug in the 5, get 220 and 5/6. They plug in the 2 and get 15 1/3. Then they do the same thing for the z's. They plug in 5 and get 20. Plug in 2 and get 2. and then they do the same thing for the y's, and then they do the same thing for the z's. Plug in 5 minus what you get when you plug in 2. Notice that's going to give you the exact same vector value as we got here. So some people like to write this step this way. Other people like to write that step this way. I kind of like this vector minus vector. Plug in the 5s, get a vector, subtract, plug in the 2s, get a vector. So that's how we do a definite integral with a vector valued function. Now, the last concept that we're going to look at in this section is the concept of arc length. So vector valued functions give curves in space. We want to find the arc length of the curve from one point to another. So how do we go about finding arc length? If r of t is a vector valued function and it has continuous derivative from a to b, then we can find the arc length, which we call L, of the graph from a to b by integrating the length of the derivative of our vector valued function. So we take our vector valued function, take the derivative, take the magnitude of that, and integrate it from a to b. By the way, the magnitude means that we're going to be calculating a single function, a real function here. So when I integrate, I'm going to get out a real number as long as I can integrate it. So arc length is given by integrating from a to b the magnitude of the derivative. Just so we're on the same page, the arc length, what we're talking about is the length of how far an object would travel along a path. So how far an object would travel along a path if the vector valued function determined my path. Let's do an example of this. Let's find the arc length of 2 cosine t, 3 sine t, t on the interval 0 to pi. Now, when I do this, fair warning, I'm going to use the integration feature on my calculator to simplify it so I don't have to do it by hand. But I will integrate and I'll use my calculator and get an approximate answer. So let's find that arc length. Now we've dealt with this function before, this vector valued function, so we should be comfortable with doing the derivative. Derivative of 2 cosine of t is -2 times sine of t. Derivative of 3 sine of t is 3 cosine of t, and the derivative of t is 1. And we're going to be doing the arc length on the interval 0 to pi. Now this 0 to pi means that the t goes from 0, a t value of 0, to a t value of pi. So we're going to be integrating from 0 to pi. I'm going to leave that as b right now, a and b. Okay. Now, when you integrate, I'm going to integrate the magnitude of the derivative. So remember how to do magnitude of the derivative. We're going to take the square root of the x component squared. So that's going to be -2 sine of t all squared plus the y component squared. That's going to be 3 cosine of t all squared plus 1 squared. And we're going to do that with respect to t. That was out. If you want to do this by hand, that's a pretty difficult problem to do by hand, but you can do it using technology and get an approximate answer. Maybe I should say that. Make sure if you're doing this on a calculator that you are in radian mode. So I'm going to go ahead and do that. Integrating 0 to pi of the square root of -2 times sine of t, quantity squared, plus 3 times cosine of t, quantity squared, plus 1 squared with respect to t. I got approximately 8.54. That is rounding to 2 decimal places. Hopefully I typed that in right. I think I did. And hopefully you can also type that in. If your calculator doesn't like the variable t, obviously you can use the variable t if you want. You can also use any other variable. If your calculator prefers the variable x, just replace the t with an x and do your calculations that way. But that's what we get. Our arc length is about 8.54. That is from 0 to pi. Visually, we looked at tangent lines earlier of this same exact graph. So we saw that at t value of pi over 3, we got a tangent line that looks like this. This time we're finding arc length. So specifically the arc length from 0 to pi. If you look down on this, look down on the z-axis, you see that it's basically like a half of an ellipse looking down, but it also gains height as it goes up as well. So if we took this green little piece here out of our bigger graph, we're asking how long would this green piece be? In other words, if I have a string that goes from here along the z and stops here, how long would that string be? Another way to think of it is if I have an object moving in space, let's say it's moving down a slide from, let's say here, down a slide that curves around and stops here, how long would that, or how far would that object have traveled? So that's the idea of arc length. Arc length is pretty straightforward, integrating the magnitude of the derivative. integrating magnitude of the derivative. So we saw a lot of things in this section. We saw arc length. We saw how to do definite integrals. We saw how to find specific antiderivatives. We saw how to find the class of antiderivatives, which is the indefinite integral, how to find the indefinite integral, how to find definite integrals, how to find specific antiderivatives. We found some rules for derivatives and some properties for those derivatives, and also how tangent lines worked with derivatives in three-dimensional space, how limits worked and continuity works in three-dimensional space. So a lot of our basic ideas of calculus can be applied naturally to our vector valued functions. And that's what we did in this video.